Today in Chapter 7, we're going to take a look at ways to classify reactions and other ways to classify reactions. We're almost finished with the chapter, about ready for a test next week. Driving forces for a reaction. We talked about this already. Formation of a solid, formation of water, transfer of electrons, and formation of a gas are all driving forces or things that cause reactions to go. So we talked about formation of a solid being a precipitation reaction, formation of water is an acid-base reaction, transfer of electrons is our redox reaction. We're going to look at formation of a gas today, and we're going to learn how to classify these so we can identify them better. You know that a precipitation reaction is just a formation of a solid, and this happens when two solutions are mixed, and this is the solution we started off with, or the equation we started off with earlier in the chapter. So this was our precipitation reaction with an aqueous and an aqueous, yielding a solid and an aqueous. So we can classify this as a precipitation reaction. We also can classify this as a double displacement reaction or the double date switch. Now, you can remember it as the double date switch. However, when it comes to the test, you have to know it's a double displacement reaction. So we have A, B, so potassium and the chromate. Potassium would be A, chromate would be B. C, D, barium is C, the nitrate is D, and they're going to switch partners. Remember that we talked about you had to make sure that your positives always switched and ended up with a negative. So we have A's and C's that are positive in this case, and our negatives are going to be B and D. So when you get finished, you have to make sure that you still have a positive and a negative together to show the switch. So when I see this reaction, I can classify it as a precipitation reaction and also a double displacement reaction. Acid-base reactions involve hydrogen ions that end up in as water in the product. We talked about this reaction right here being our net ionic equation for an acid-base reaction, a strong acid and base reaction. So our hydrogen ion and our hydroxide ion go together to form our liquid water, and we know this ionic compound right here to be known as a salt. So we have hydrochloric acid, potassium hydroxide, yielding water, and a salt, which is a positive ion and a negative ion. We just need to remember to be able to recognize it as an acid-base reaction, and this is the type of thing that we're looking for. So we can classify this one as acid-base. We talked about oxidation reduction reactions or redox reactions, and this is where we transfer electrons. So we started off with lithium, and lithium has a zero charge, just like we talked about magnesium or the sodium having a zero charge to start with. It's a solid. And we have fluorine gas in this case, and it has a zero charge. Lithium becomes +1, fluorine is going to become -1, so they're going to go together 1 to 1. And even though we have 2 fluorine here, we take care of that balancing by putting the 2 coefficient out in front and the 2 in front of the lithium. So this is a redox reaction, which is a transfer of electrons. Another type of redox reaction is called formation of a gas, and it's also an example of a single replacement reaction most times as well. Here's an example of that. We have zinc solid, which is uncharged. We have hydrochloric acid that's aqueous, and we know that that's really broken up into its ions. And it forms hydrogen gas and zinc chloride, or zinc 2 chloride, and that's aqueous. So it forms this gas. So we have a zero charge going to a charge over here, because it's a zero charge going to a +2 because it reacted with the chlorine. And we have 2 that have charges here, and the hydrogen goes from a +1 charge to a charge of 0. It's uncharged. So this is a redox reaction because it is changing charges on some of the elements involved. It's a single replacement reaction because we have zinc who actually replaces hydrogen and pairs up with chlorine here. So it's a single replacement reaction. And you notice it's also the production of a gas, which is another indicator that it's also a redox reaction. Here's an example similar to the picture we had in the earlier lecture about what's actually going on, so you can tell where those electrons are going. So let's look at other ways to classify reactions to kind of put this whole idea of how to classify together. So we're going to start with looking at all kinds of reactions and lumping them into the group chemical reactions. We can branch chemical reactions off into precipitation reactions, which you should be able to recognize, oxidation-reduction reactions, and acid-base reactions. So you should be able to identify those three types of reactions. Combustion reactions, you can further classify that as a combustion reaction sometimes if it's a redox reaction. So not all redox reactions are combustion, but all combustion are oxidation-reduction reactions. Let's look at a synthesis reaction, a compound that forms from simpler materials. This is actually a special case of oxidation-reduction reactions. We have carbon, and it's a solid, and we have oxygen gas, and it's in the gaseous state as a molecule, and that'll have a zero charge and a zero charge here, and it's going to share electrons here and have a little bit of a charge. So you don't really have the transfer like we had in an ionic compound. We have this nonpolar sharing, actually, is what's going on here. But one of the things that makes it a special redox reaction, because it's not a metal and a nonmetal, is the fact that we have plus O2 right here, and that is has oxygen gas or a gas involved in it that allows for combustion. So combustion reactions are also redox. Another thing that it is putting together a single element and a single element. Well, it's the best single oxygen can be. It's diatomic. So a single and a single to form a compound. So A plus B yields AB, and that's an example of synthesis. We have decomposition reactions that are also special redox reactions. In this case, we have water breaking down into its components. So you see that we have, this is a non-polar sharing here going on. So we don't really have charged ions like we said before. We have some unequal sharing, but not like a metal and a nonmetal together. And we end up with two different ones that are have an overall charge of 0. This is decomposition because it's taking one compound and it's breaking it down into its component elements. So that's a sign that it's an oxidation-reduction reaction. And again, we have oxygen produces a gas, and that is an indication of redox reaction as well. So if we take a look at this overall picture, we see that we can take chemical reactions and we can identify them as precipitation, as oxidation reduction, or as acid-base reactions. If they are precipitation or acid-base reactions, you can stop there. You don't have to classify them any further unless you're going to classify them as the double displacement reactions, which we expect both of these to be. The oxidation reduction reactions, once you identify that, you need to look at it and see if it's a combustion reaction, if it's a synthesis, or if it's a decomposition, or it could be a combination. So redox gets a little bit more complicated to classify, but it's just knowing what it is to be able to recognize it. So let's look at the concept check. The reaction between hydrogen and oxygen to form water. This can be classified as what type of reaction. So you just have to look at it and say, okay, what am I dealing with? First of all, just start and ask yourself, is it a precipitation reaction? Do we have an aqueous plus an aqueous yields a solid and an aqueous where we have the double date switch? And that's not happening. The next thing that you ask yourself is it an acid-base reaction? Is that what's going on? So do I have an acid plus a base and it yields liquid water and a salt? And we have water here, not sure what the state of it is. I'm assuming that it's liquid, but we don't have the salt produced, and we don't have hydroxide or hydrogen ions to be given up on this side, so it's not an acid base. This overall charge is a 0 to begin with because it's not combined with anything else, and it's diatomic. This one is as well. And then we have the special sharing that goes on with this nonpolar bond here with the water molecule. So another indicator we have, if you look at it and say this must be a redox, it's because it's a synthesis reaction. 1 plus 1 yields a whole new compound. So this is the elemental yields the compound. So, and also oxygen is involved here as a reactant or a product, and that tends to tell us that it's also a redox reaction. Let's see what they give us as possibilities. So is it redox? Is it synthesis? Is it combustion? And the answer is, it's all of the above. Because plus O2 is your indicator that it's a combustion reaction. So for the last two sections, there's not any real easy way to tell you how to do the problems, and it may seem a little overwhelming. I'm telling you that the best help that you can use for this, here it is, right here, is this chart that I know is in your textbook. That helps you put it into perspective as far as keeping them separated a little bit better. One of the things I do want to bring out is that in addition to, let's see if I can switch over to the pen, not that you'll be able to read it, but I can try it. So in addition to what you see here, something else that could be labeled is your double displacement. So I'm just going to put the DD reaction, double displacement. This is a double displacement reaction as well as an acid-base reaction. So I could say what kind of chemical reaction it is. You would say it's precipitation and it's double displacement. That's true statement. Or it's acid-base and it's a double displacement reaction. The other one is the single replacement reaction, and that's only going to happen in the redox world. So it's possible to also have a single displacement reaction down here as well. So just keep an eye out for those, and that's all the labeling that you're going to have to do is just to identify them like that. Just remember that you cannot say the precipitation reaction is going to be combustion or acid-base is going to be decomposition. You're not going to see that happen. So just get familiar with what you're looking for, know what characteristics you're looking for, and do the best you can.